Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. Have you ever stood under a vast, endless night sky, staring into that sea of stars, and felt something stir inside you? A deep, almost ancient longing. What if, circling one of those distant suns, there was a planet where winds whisper across? Alien oceans or civilizations thrive under colors we cannot even imagine. Right now, as you listen to these words, somewhere out there, those worlds could be orbiting in silence, waiting for someone or something to find them. Humanity has always wondered about life beyond Earth, but today, for the first time, we are not just wondering, we are searching. And the greatest tool in this search is the James Webb Space Telescope. For thousands of years, humans thought the stars were fixed, divine lanterns hung in the heavens. Philosophers like Epicurus speculated about infinite worlds, but it remained just that, a speculation. Even into the early 20th century, the idea of planets beyond our solar system was the stuff of myth. It wasn't until the year 1992 that the first confirmed exoplanets were discovered. Orbiting a pulsar, a dead, rapidly spinning neutron star, thousands of light-years away. This discovery stunned astronomers. It shattered the idea that planets formed only around young, healthy stars. It also hinted at a larger truth. If planets could form around something as extreme as a pulsar, maybe planets were common across the galaxy. Then, in 1995, came the detection of 51 Pegasi b, the first planet found orbiting a sun-like star. It was a hot Jupiter, a gas giant larger than Jupiter, orbiting blisteringly close to its star. At first, astronomers were baffled. Planets like that shouldn't exist according to our models. But it was real, and it opened the floodgates. Over the next 2 decades, missions like Kepler and TESS, the Transiting Exoplanet Survey satellite, revealed that planets are everywhere. Some sun-like stars have multiple planets. Some rogue planets drift between stars, unbound by any sun. There are lava worlds, ice worlds, gas dwarfs, super-Earths, and Earth twins. The more we looked, the more the universe began to look populated. And yet there was a catch. Finding planets was only the first step. Knowing what they were like, whether they could support life, was a far harder question. That's where the James Webb Space Telescope comes in. The JWST is not just a better telescope, it's a fundamentally different kind of machine. Where the Hubble Space Telescope, the HST, captured beautiful images in visible and ultraviolet light, the JWST sees the universe in infrared. Why does this matter? Imagine a campfire viewed from a distance. Even after the flames die down, you can feel the heat. Infrared light is the heat signature of objects, planets, dust clouds, even galaxies, glowing faintly against the cold backdrop of space. Many of the most interesting exoplanets, especially small rocky ones, are shrouded in dusty regions or orbit dim stars. They are invisible to regular telescopes, but in infrared, they shine like embers in the dark. Now imagine this, a star far away shining steadily. Suddenly its brightness dips ever so slightly, a fraction of a fraction. It dips because a planet is passing in front of it, blocking a tiny piece of the light. This is called the transit method, and it's one of the most powerful ways we find exoplanets. But the JWST takes it even further. As the starlight passes through the thin layer of atmosphere around the planet, certain wavelengths of light are absorbed by specific molecules. Water vapor, methane, carbon dioxide, even oxygen. By spreading the light into a spectrum, like a cosmic fingerprint, scientists can tell exactly what the atmosphere is made of. Think about that for a moment. We can now analyze the air of a planet that may be hundreds, even thousands of light years away. We can detect if it has clouds, storms, haze, or even oceans. If there's methane alongside oxygen, it might even suggest life, because on Earth, methane and oxygen together are constantly produced and consumed by living organisms. The JWST is our best shot yet at finding these biosignatures, and the evidence is already thrilling. When the JWST turned its gaze to WASP-39b, a planet 700 light-years from Earth, it did not just see a shadow. It read the chemistry of an alien sky. It found clear evidence of carbon dioxide, making it the first time in history that this molecule was directly detected in an exoplanet's atmosphere. This might sound small, but it's a giant leap. It proves that the tools work. It proves that we can peel back the veil of alien atmospheres and read their secrets. But what about Earth-like planets? That's the real prize, the holy grail of astronomy. Small, rocky, temperate worlds where liquid water can exist. Some of these worlds orbit red dwarfs, small dim stars where habitable zones are much closer in. Others might orbit stars like our own sun. And with the JWST, we can finally start characterizing these worlds. It will not be easy. Detecting the tiny signals from such planets is like trying to spot a moth circling a floodlight from thousands of miles away. But for the first time in history, we have a machine built precisely for that challenge. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free and it helps us grow this community together. Your interest, your passion for discovery, is the fuel that pushes us deeper into the unknown. You are part of this incredible journey, and together, we'll stand at the threshold of the greatest discoveries of our age. As we move forward, we'll explore exactly how these hidden worlds are discovered. We'll dive into the science behind the transit method and gravitational microlensing, uncover the strategies researchers use to read the light of alien skies, and meet the incredible teams, bringing us closer to the answer to the oldest question of all. Are we alone? So get ready, because the universe is more alive and more mysterious than we ever dared to dream. Imagine you are an astronomer, a detective of the stars. Somewhere in the endless night sky, there are planets waiting to be found. But you can't simply point a telescope and see them. Not yet. Even the largest, brightest exoplanets are drowned out by the furious blaze of their parent stars, like fireflies lost in a floodlight. So how do you find a planet you cannot see? How do you hunt a ghost in the dark? You look for its shadows and its gravitational fingerprints. The two most powerful methods astronomers use to uncover distant worlds are known as the transit method and gravitational microlensing. These techniques have transformed exoplanet science from pure speculation into a thriving field of discovery. And now, the James Webb Space Telescope stands ready to push these methods to their ultimate limits. Let's start with the transit method, the primary tool in our cosmic toolkit. Picture a tiny planet orbiting its star. Once every orbit, from our perspective, the planet crosses, or transits, in front of the star's face. For a few precious hours, the planet blocks a minuscule fraction of the star's light. If you were watching a star like the Sun from another star system, Earth's transit would dim its light by just 84 parts per million, less than 1/100%. That's like noticing a flea crawling across a car's headlight from several miles away. Yet with precision instruments like the JWST, we can detect these infinitesimal dips with breathtaking accuracy. But detection is just the first step. The magic happens when the starlight passes through the planet's atmosphere. Different molecules absorb different wavelengths of light. Water vapor leaves one fingerprint, methane another, carbon dioxide still another. By capturing and analyzing the starlight during a transit, scientists can decode the chemical composition of an exoplanet's sky, its clouds, its hazes, its potential for life. Take TRAPPIST-1e, TRAPPIST-1e, a rocky, Earth-sized planet orbiting within the habitable zone of a cool red dwarf star. If life exists anywhere beyond our solar system, it could be in places like this. The JWST is already targeting TRAPPIST system worlds, examining their atmospheres for signs of water, carbon-bearing molecules and temperature patterns that could hint at conditions favorable to life. Imagine we are standing on the edge of perhaps the most important discovery in human history, and then there's gravitational microlensing, a method so strange, so elegant, it sounds like pure science fiction. But it's real, and it's rooted in Einstein's theory of general relativity. Here's how it works. Gravity bends space. A massive object, like a star or even a planet, warps the very fabric of the cosmos around it. If a foreground star passes precisely in front of a background star, its gravity acts like a magnifying glass, bending and focusing the background star's light. And if that foreground star has planets, they create tiny detectable blips in the light curve. Think about the scale of precision needed. 2 stars, separated by light years, lining up perfectly for just a moment in cosmic time. It's a cosmic coincidence, a fleeting whisper of a hidden world. Yet with careful monitoring, and with the unparalleled sensitivity of the JWST, these micro-lensing events can reveal planets too small, too distant, or too cold to be found by any other means. Rogue planets, icy wanderers untethered from any star, can be found this way, offering a glimpse into the wild, free-floating worlds adrift in the dark. But hunting exoplanets is not just about collecting data. It's about interpreting clues in a grand cosmic mystery. When scientists examine a transit or a micro-lensing event, they don't just get a name and a distance. They uncover hints about size, mass, density, temperature, atmosphere, and even weather patterns. In some cases, they might glimpse clouds of ammonia crystals or detect variations in light that suggest turbulent, storm-racked skies. With enough transits observed over time, astronomers can even estimate the presence of moons or rings surrounding distant worlds. And it is not just single planets anymore. New discoveries increasingly reveal multi-planet systems. Entire families of planets dancing around their suns in intricate gravitational ballets. Some systems are crowded with planets orbiting closer than Mercury orbits our Sun. Others stretch out with planets at frozen distances. Each system is a fingerprint of its star's history, and each one challenges our understanding of what planetary systems can look like. The James Webb Space Telescope enhances every part of this detective work. With its incredible infrared sensitivity and sharp spectroscopic instruments, it captures the faintest signatures, even from planets hundreds of light-years away. And because it operates beyond Earth's atmosphere, free from its distortions and noise, its observations are pure, clean, and astonishingly deep. Already, early results from the JWST have stunned astronomers. They have detected unexpected chemicals in exoplanet atmospheres, uncovered wildly exotic climates, and hinted that rocky worlds may be far more common and far more diverse than we ever dared to hope. We are not merely cataloguing distant dots anymore. We are starting to know these planets, to read their skies, feel their climates, and maybe someday soon recognize a living world. As we move into the next chapter of this incredible story, we'll turn our gaze specifically to the technology itself. What makes the JWST so uniquely powerful? How do its mirror segments, its sunshield, and its spectrographs come together to transform faint cosmic signals into groundbreaking discoveries? We'll take you inside the mechanics of this one-of-a-kind space observatory and reveal how it brings the universe into focus, one fragile, brilliant photon at a time. Now, let's take a step back and look at the James Webb Space Telescope itself. You've heard about its revolutionary science and its role in hunting for exoplanets, but what makes it so powerful? How does this incredible machine peel back the cosmic curtain and reveal the secrets of distant worlds? To understand the JWST, we must first understand what it took to build a telescope that could change the future of astronomy. Imagine a telescope that could not only observe distant stars and planets, but see them in ways that no one had ever imagined. The key to the JWST lies in its infrared vision. Regular telescopes like the Hubble Space Telescope can see invisible light, the same light that our eyes can detect. But to peer deeper into space, we need to look beyond visible light into the infrared spectrum. Why? Because infrared radiation can penetrate through cosmic dust clouds that obscure visible light. It allows us to observe objects that are too cold or too distant to be detected otherwise. Objects like newly forming stars, distant galaxies, and exoplanets with their alien atmospheres. But to capture these faint infrared signals from across the universe, the JWST had to be built with cutting-edge technology. Its mirror, at an impressive 6.5 meters across, is nearly 3 times the size of Hubble's mirror. That gives it a light-gathering power that allows it to collect photons from some of the faintest objects in the universe. The challenge, however, wasn't just in size, it was in precision. The JWST uses 18 hexagonal segments that unfold like a flower, each piece precisely aligned to create a single unified mirror. This folding and unfolding process is a masterpiece of engineering, and it had to work perfectly because the telescope was too large to fit in a rocket as one whole piece. Now imagine you're standing on the ground, watching this massive telescope unfold in the vacuum of space. It's not just the mirror that makes this telescope so unique, it's the sun shield. The JWST carries a sun shield the size of a tennis court, a 5-layered structure designed to protect its delicate instruments from the heat and light of the sun. It's as thin as a human hair, yet capable of keeping the telescope cool, enough to detect the faintest infrared signals. Without this shield, the heat from the sun would drown out the very signals we need to observe. But how does the JWST actually detect these signals? Through its scientific instruments, of course. At the heart of the telescope's science are 4 key instruments: the near-infrared camera, NIRCam, the near-infrared spectrograph, NIRSpec, the mid-infrared instrument, MIRI, and the fine guidance, sensor near-infrared imager, and slitless spectrograph, FGS NIRIS. Each of these instruments serves a different purpose, giving the JWST the ability to capture a wide range of data from the universe. The NIRCam is one of the most crucial instruments for exoplanet science. It allows the telescope to capture sharp, high-resolution images in the infrared. This is essential when observing distant exoplanets, allowing scientists to detect their presence even when they are extremely faint. The NIRSpec, on the other hand, is designed to capture spectra, the unique light signatures of different molecules. This instrument can measure the chemical composition of exoplanet atmospheres by analyzing the way light passes through them during a transit. The MIRI is the telescope's mid-infrared camera, and it can look at even colder objects like gas giants or distant faint stars. Finally, the FGS NIRIS is used to fine-tune the telescope's focus and also provides critical data for detecting distant exoplanets by capturing their light and spectral information. Now imagine all these instruments working in harmony, each one finely tuned to capture a different piece of the cosmic puzzle. Together, they make the James Webb Space Telescope not just a tool, but a symphony of technological marvels. With its instruments, the JWST can peer into the birthplaces of stars, look at galaxies formed billions of years ago, and for the first time, analyze the atmospheres of alien worlds with unprecedented detail. But to capture those faint signals, the JWST needed to go to a place unlike anything we've used before. The Hubble Space Telescope orbits Earth, but that means its observations are affected by our atmosphere, the shifting weather patterns, and the light pollution of our own planet. The JWST is not in Earth's orbit. It's located at the second Lagrange point L2, about 1.5 million kilometers away from Earth. This unique location allows the telescope to remain in a stable orbit, keeping its instruments cold and shielded from the Sun, Earth, and Moon's heat and light. It also gives it a clear view of the entire universe, free from the distortions caused by Earth's atmosphere. At L2, the JWST has a panoramic view of the cosmos, and it's not just waiting for signals, it's actively collecting them. It will look at exoplanets as they transit their stars, collecting data on their size, atmosphere, and potential for life. It will study distant stars and galaxies, revealing the origins of our universe. The data it sends back will fuel years, if not decades, of research, and open up entire new areas of science that we can't even fully comprehend yet. Imagine being part of a team of scientists receiving data from a telescope light years away. Each new bit of information reveals another layer of the mystery. Could this world support life? Is there water in the atmosphere? Is it Earth-like, or something else entirely? The thrill of discovery, of pulling a secret from the heart of the universe, is now in our hands thanks to the unprecedented capabilities of the JWST. And while this sounds like the end of the story, we've only just begun. The JWST will be at the forefront of a new era in astronomy. The discoveries it uncovers will be profound, challenging, and awe-inspiring. But the real question is, what will we find? The universe is filled with wonders we can't yet imagine. We're standing at the edge of discovery, about to peer deeper into space than ever before. And with every observation, every new planet discovered and every distant galaxy revealed, the universe becomes a little smaller, a little more familiar. So, what else is out there? What other secrets are hidden in the far reaches of space, waiting for the JWST to uncover? The journey is just beginning, and it's a journey we'll take together. Now that we've explored how the James Webb Space Telescope will revolutionize our understanding of exoplanets, let's step back and think about the bigger picture. What does all this mean? What do the discoveries of distant planets, strange, new atmospheres and alien worlds really tell us about our place in the cosmos? We've already established that the JWST will provide us with the most detailed, most accurate pictures of exoplanets we've ever seen. But let's push further. Imagine what these discoveries could mean for the future of humanity. For centuries, we've looked up at the stars and wondered, are we alone? Now we're on the brink of answering that question in a way we never thought possible. The truth is, the hunt for exoplanets is more than just scientific curiosity. It's a search for meaning. It's an attempt to understand whether the Earth is a unique jewel in the vastness of the universe, or just one of many worlds capable of supporting life. The discovery of even a single Earth-like exoplanet could be transformative. If we find a planet with a similar atmosphere to ours, if we detect signs of water, or if we glimpse a world that might host life, it could change everything. We'd no longer be alone in the universe. For the first time, we could be standing at the doorstep of an entirely new chapter in the history of humanity. Perhaps one day, we might even make contact with another intelligent species, or discover traces of their civilizations. The implications for science, philosophy, and even our sense of self are profound. But let's zoom out even further. Think about this. How many times in history has humanity taken a step forward, only to have its understanding of reality completely rewritten? Remember when we thought the Earth was the center of the universe? Or when the solar system was just a small, unimportant corner of the Milky Way? Every time we make a major discovery, whether it's the heliocentric model of the solar system, the theory of evolution, or the nature of space-time itself, we don't just gain new knowledge. We completely reframe our understanding of the universe and our place within it. In the same way, the search for exoplanets could be a turning point in human history. As we discover more and more alien worlds, we'll gain a deeper understanding of how planets form, how life might emerge, and whether there are infinite possibilities for life beyond our own tiny world. With each new discovery, we'll redefine our role in the cosmic theater, shifting from beings at the center of the universe to just one thread in the vast tapestry of space and time. But it's not just about finding life. The study of exoplanets is teaching us more about our own planet, too. By understanding how other planets behave, by comparing the atmospheres of distant worlds to Earth's, we can learn more about the future of our own planet. We might uncover signs of climate change in alien atmospheres, helping us understand the long-term impacts of our own environmental decisions. We might even find planets that have undergone processes similar to Earth's, giving us insights into how life might evolve, or how a planet might lose its ability to support life. Every exoplanet is a potential mirror that reflects a different facet of our own world's past, present, and future. And that's where the human element comes in. All of these discoveries, all of this new knowledge, brings us back to a question that has haunted us for centuries. What is our purpose? When we look at Earth, we see beauty, complexity, and fragility. We see the delicate balance of ecosystems, the intricacy of human life, and the history of countless civilizations. When we look at the stars, we wonder if any of those distant worlds are home to something similar. We wonder if another species on another planet is asking the same questions we are. The discovery of alien life, or even just the knowledge that life is possible elsewhere, could force us to confront our place in the universe. It would remind us of the preciousness of life itself and our responsibility to protect the world we call home. It would push us to look beyond our borders, to work together as a species, and to explore not just the stars, but the nature of life itself. But we're not there yet. This is just the beginning. The James Webb Space Telescope will lead the charge in answering some of the most fundamental questions we've ever asked. As we scan the skies, we'll see worlds that have never been seen before. We'll unlock the secrets of alien atmospheres, distant stars and cosmic phenomena that have been hidden for billions of years. Every new discovery will build on the last, and soon we'll have a clearer picture of what exists in the vast dark. But even more exciting is the possibility that we are just scratching the surface. The universe is enormous. There are billions of stars, each with its own planets, moons, and mysteries. The JWST is just one tool, a powerful one, but there are more to come. As technology evolves, as future telescopes and space missions come online, we will see even further, understand even more. Perhaps one day we will build a civilization that spans the stars. Perhaps we will find new worlds to call home and new life to share our journey with. Or perhaps we'll simply continue to explore, to ask, to learn, and in the process uncover the greatest mystery of all. What's out there? So, what do you think? Are we truly alone, or is the universe teeming with life, waiting for us to find it? The James Webb Space Telescope will bring us one step closer to the answer. The journey of discovery is just beginning, and you are part of it. If you've been as captivated by this adventure as we have, then share this video. Comment your thoughts, your questions, your wildest speculations. Let's dive into this conversation together. What worlds will the JWST reveal next? The universe is calling. Are you ready to answer?